All right, everybody, welcome to my thesis presentation. I want to just extend my gratitude for you all joining. The title of my work is called Grounded or Guessing, an empirical evaluation of LLM reasoning in agentic workflows for root cause analysis in cloud-based systems. So I'll just jump right in. So I'll start with the background and motivation. I'll cover what root cause analysis is, why it's difficult, and why the capabilities of LLMs to perform RCA remains a bit unclear. Then I'll describe our methodology and experimental framework, present the results, close with some discussion points along with the limitations and threats to validity. So with that, let's start with a real-world example. So on October 24th of this year, AWS suffered a pretty massive outage that took down a large chunk of the internet, including Snapchat, Fortnite, Alexa, Ring, and Coinbase for about 16 hours. And it turns out that the root cause was actually a race condition within an internal DNS management system. And this concurrency bug caused the system to delete active DNS records, which then cascaded outward, causing widespread connectivity loss that affected millions of users. And this illustrates a critical problem. So small faults can trigger massive nonlinear consequences. A small issue or misconfiguration in one component can cascade and cause widespread system disruption. Now, of course, not all take out half the internet, but detecting the originating fault quickly is essential for uptime and cost control. And finding that needle in the haystack is the real challenge. And that's really the practical importance of what we refer to as root cause analysis, or RCA for short. The objective of RCA is to identify the underlying fault that produced the symptoms or failures that we observed. Here, a failure can refer to really any kind of incorrect or anomalous system behavior, like offline components, network congestion, or resource exhaustion, just to name a few. And more specifically, it's an a posteriori process because we're trying to investigate and understand events that have already occurred. So our task is to gather the evidence, in this case, the observed symptoms, and map them to fault hypotheses that could plausibly explain them. So we're analyzing real incident data from a live production incident to explain what happened, where it happened, and why it happened. Now, more formally, we define this as two subtasks: root cause localization, so the where, and fault type classification, which is the what. And to figure out the location and type of fault that occurred, we treat this as a data-driven analysis task. So primary data is the data collected while the system is running, and we refer to this as telemetry data. And it relies on three main pillars: logs, which are structured or unstructured records of discrete events within the system; metrics, which are quantitative measurements reflecting system performance over time; and traces, which are records that capture the end-to-end flow of a request through the system's components. Now, it's often helpful to also consider supplementary information for additional context. So things like events, such as user or incident reports, or topological information, which can provide a useful map of how entities connect or interact to better understand how a failure might propagate. And of course, there's lots of other types of knowledge that might be helpful. Now, as you might be able to imagine at this point, RCA is extremely challenging for a few reasons. Firstly, the utter scale and volume of telemetry data that is produced can be very, very overwhelming, and retrieving useful data points can be quite tough. Another is partial observability. So not all system components are emitting telemetry data at the level of granularity that's required for RCA. So this could be because of sampling frequency or data retention limits or instrumentation gaps. So critical evidence might simply just be missing. Now, cloud-native systems are often modular and ever-changing. This makes them evolve quickly, and similarly for their topologies and dependency structures. And last but not least is fault propagation and cascading failures. These often make it difficult to understand where the real root cause occurred. So as you see in this graph on the right, symptoms can really appear anywhere in the system, like in nodes D, K, and O. But that doesn't mean that those were the problem. We need to be able to trace the propagation path back to the root cause, and in this case, node M. So these factors are why we want automated but interpretable procedures for root cause analysis. Now, lots of people have started to look at and integrate LLMs into RCA pipelines. Because of their reasoning and tool use capabilities, LLMs offer the potential to navigate system knowledge and extract insights from both structured and unstructured data. They can also provide explainable and traceable steps for how they arrived at their final answer. And LLMs really do look incredibly promising for RCA, but we don't have a great understanding of how good these models are at the core RCA task. And it's important that we get to the bottom of this if we're going to be deploying them in production level systems. So the reason for this lack of understanding is due to shortcomings from 2 points of view, from an empirical point of view and from an evaluation point of view. So empirically, many current approaches mix multiple tasks beyond the RCA task, like anomaly detection or code execution or multi-agent coordination. So it's unclear whether errors come from the LLM's reasoning or if it's from auxiliary components or peripheral design decisions. So this creates a sort of entanglement of all of these different factors and makes that attribution difficult. Now, from an evaluation point of view, most work report on final accuracy. So they look at how well an LLM-based approach was able to recover the known root cause location and type. But they tend to overlook the quality and the correctness of the model's reasoning or the claimed propagation path. So they check if the agent guessed the right fault, but they don't check why. And this means an agent could be right for the wrong reasons, which can be dangerous in production settings. So the central question is, when all of these confounding factors are stripped away, how adept are LLMs really at performing root cause analysis? So to answer this question, how adept are they really, we need to address both of these shortcomings. In our work, we design a controlled experimental framework in which we purposefully simplify the environment to isolate the LLM's reasoning about the RCA task and remove those confounding factors. The model gets pre-extracted anomaly alerts, a typed knowledge graph for context, and we use simple agent architectures with deterministic tools. So this lets us attribute failures to the model's inference rather than to the plumbing. So there's no open-ended code execution or multi-agent coordination or system-specific heuristics that make this attribution difficult. We also address the evaluation issue. We contribute a systematic evaluation method for investigating root cause analysis reasoning quality. And we do this by identifying common reasoning failures, and we use an LLM as a judge for identifying these. So with all that said, we have 4 research questions that focus our empirical evaluation. First is, how effectively can an LLM agent perform RCA tasks? So this is more from an outcome correctness perspective. 2 is, how sensitive or final RCA outcomes to alert modalities? Third, what reasoning failures appear in agent inference traces? And lastly, how does the presence of reasoning failures affect the likelihood of generating correct RCA hypotheses? So we have 3 key contributions: an evaluation framework that isolates LLM reasoning, a human-rated LLM as a judge to identify reasoning failures, and an extensive empirical study. We evaluated 48,000 samples that required 228 days of unparalleled execution time. All right, let me move on to the methodology. So our study method consists broadly of 3 stages: data preparation, RCA inference, and evaluation. And let me first explain these at a high level. So the objective of the data preparation stage is to produce a set of telemetry alerts and construct a system knowledge graph. And these form the inputs into the RCA inference stage, where we invoke an LLM to perform root cause analysis, and its task is to produce a set of root cause hypotheses. And then using these, we evaluate output quality and reasoning quality. Let's look closer at the data preparation stage. The first objective of this stage is to produce a set of alerts for a given fault from raw telemetry data. And the reason we extract alerts is to make sure that the LLM only has to focus on the RCA task, so it doesn't also have to do anomaly detection, which is really a whole task on its own. And we ensure that the failure information it receives can fit into its context window. So we give it the most important signals. So we start from raw telemetry data. So for each modality, we extract anomalous behavior as these alerts. So for traces, we look at two features, response times and error status codes between entities. So if the average response time is higher than normal, we create a performance degradation or PD alert. And if the volume of error codes of requests between a set of entities is anomalous, then we also create an alert like this 500 status error code. Now for logs, we create alerts from error logs and from lower frequency logs. So the idea behind the lower frequency logs is that these may capture rare execution paths or edge case behavior or error handling logic that may not appear during normal operation. And for metrics, we do a time series analysis and simply pick out periods where a metric was significantly above or below its regular operational values. And then lastly, we put this all together into a unified textual representation that we can then pass to the LLM. Now, the other part of the data preparation stage is knowledge graph construction. So the intention of this knowledge graph is to capture the relationships between system entities to help with understanding how a fault might propagate through the system. So to do this, we use data flow and control flow dependencies and deployment configurations. So we look at documentation, manifest files, and deployment files. And for the purpose of this study, we do that construction manually to ensure correctness and completeness. Now for the RCA inference stage, we deploy an LLM in 3 workflows: straight shot workflow, which is a non-agentic baseline where an LLM simply reasons and then returns the root cause hypotheses. React, the LLM now has access to the environment and goes through thought, action, and observation loops. And then lastly, the plan and execute workflow, which is similar to React, but first plans and then executes each step of the plan. Now, the agentic workflows, so the React and plan and execute workflows, have access to the environment where they can take actions. So the action space available to these LLMs in those workflows are defined by 6 tools. Their purpose is to expose entity relationships and the system's topology that is encoded in the knowledge graph. So we have 2 categories: tools that provide characteristics of specific entities or relationships, and the traversal tools that allow the agent to explore the structural topology of the system. Now, it's often not feasible to provide all system context to the LLM upfront, so that's why we're doing it this way. We're mimicking this type of setup by providing this information on demand. Now, I will note that for the straight shot baseline, right, the non-agentic baseline that doesn't have access to these tools, we do provide the entire knowledge graph up front, and it fits because we experiment with smaller benchmark systems, but this likely won't be the case in real production level systems. So there's value in exploring these agentic workflows. So then during RCA inference, we end up with a linear history of messages. So we start with the user query, which boils down to the main objective. Given the system knowledge graph and observed symptoms, hypothesize 3 root cause faults. Now, in all 3 workflows, the final LLM answer should contain these 3 root cause hypotheses. And in between, the LLM may have some intermediate thoughts, it might have some think tokens if it's a reasoning model, or invoke tools and receive responses back from the environment for the agentic workflows. And so this part forms the inference trace. So we then have these two artifacts produced during the RCA inference phase, the root cause hypotheses and the inference traces. Now, as the last stage, we first evaluate the root cause hypotheses using accuracy calculations. So we calculate the accuracy using the ground truth values. Since our data sets were created through intentional fault injection, we know exactly the location and the fault of the location and the type of the fault that occurred. But I'll circle back to this in a moment. But for the reasoning quality evaluation, this consists of two steps: reasoning failure elicitation and LLM as a judge evaluation. So for the first, we used a mixed methods elicitation procedure to identify recurrent reasoning failures in the form of a reasoning failure taxonomy. We performed 7 rounds of annotation with a random subset of samples, and during these rounds, we updated the taxonomy and the judge prompt. Now, once this refined taxonomy was created, we selected 3,073 random samples and tasked the LLM judge, in this case that was GPT-5, to identify the relevant failures from our taxonomy. Now, to ensure that this was reliable, we conducted a human agreement check that was done by 2 people independently on a subset of the judge data. And we observed high agreement with the judge with an agreement score of 0.92. So for the experimental setup, we considered 2 data sets collected on common microservice benchmark applications. And these data sets contain telemetry data with those known injected faults. So that provides the ground truth. We evaluate 6 LLM models with a range of sizes and model families. And we focus on open source models since RCA systems in production are typically deployed in-house for privacy and security reasons. And we consider the 3 workflows that I already mentioned, the non-agentic baseline and the 2 agentic workflows. For prompt robustness, we run each sample with different knowledge graph representations and alert unification strategies. So those are the ones listed there. We also run a set of holdout experiments wherein we withhold different alert modalities. So we exclude logs, metrics, and traces one at a time. In total, we executed 48,000 scenarios that took 228 days of unparallelized execution time. All right, let's move into the results. So to answer the first research question, how effectively can an LLM agent perform RCA tasks from an outcome perspective? We calculate the accuracy of each LLM-generated final answer. So a final answer consists of 3 root cause hypotheses, which in turn contain 4 attributes: a type, location, propagation path, and justification. And we use the first 3 to calculate the type accuracy according to the ground truth fault type, the location accuracy according to the ground truth fault location, propagation path existence, which validates whether the path is a valid walk in the knowledge graph, and hypothesis accuracy, which requires both the fault location and type to match their respective ground truth values. So we calculate accuracy as the top K accuracy with K equals to 1 and 3. And this metric looks at whether any of the top K root cause hypotheses are correct for their respective attribute. We also calculate average top K accuracy, where we simply take the average of accuracy at 1, at 2, and at 3. So we have these 2 accuracy measures for each attribute. Now let's look at the results for this research question. And the short answer is that RCA is still quite challenging for open source LLMs. And we found that simply placing a model in an agentic workflow does not guarantee or necessarily guarantee better performance. In fact, we observed either diminishing or negative returns for location, type, and hypothesis accuracies. And we even observed an increase in below random guessing performance for the react and plan execute workflows. And this was especially pronounced for small models in the fault type classification problem. Essentially, for many configurations, the added complexity of the workflow did not translate into better diagnostic accuracy or better results. Let's consider this radar plot. It plots accuracy bands across model and workflow combinations. Here, the lower bound is accuracy at 1, upper bound is accuracy at 3, and the dotted line is the average accuracy at 3. And we plot this for each accuracy metric. Now, you'll see here that the accuracy generally doesn't exceed about 50%. And it also shows that there's no one-size-fits-all winner. Performance is highly model and task specific. So for example, looking at hypothesis accuracy in red here, Quen 332b finds the correct root cause location and type most often. And so it's best for overall hypothesis synthesis. Quen 3.4b performs competitively with its larger counterpart for the baseline and React workflows. So it could be a really suitable choice for smaller systems or light deployments. And then Llama 3.3 has the highest PA and is significantly better at reconstructing the propagation path. So it could be a really suitable choice if recovering the path is the most important. And this is really where agentic workflows do help, is for these capable models, the React loop forces them to explore the graph, and this leads to higher PA values and better groundedness in the system context. But there is a catch. Look at the plan and execute accuracies for the two smallest models. They effectively plummet, and this isn't just bad performance. This is a reflection of a total breakdown. These models frequently hit execution limits or execution failures and recursion limits because they cannot perform all the tasks or skills that are required of such a workflow. So this reveals a fundamental capacity mismatch. While agentic workflows help capable models like Llama 3.3 explore, the management overhead required of the plan and execute workflow or similar overloads these smaller models. Now that we know how they perform, let's look at what data modalities are the most useful. So our second research question asks, how sensitive are final RCA outcomes to alert modalities? To answer this, we systematically withheld metrics, logs, and traces. So this delta plot shows the change in accuracy for these withholding experiments. Bars pointing down means performance got worse, and bars pointing up means performance increased. When we compare to including all the modalities. So the results actually reveal distinct roles for each modality. So looking at the orange bars in the top left panel, when we exclude metrics, location accuracy decreases. So this indicates that these quantitative metric anomalies are most effectively leveraged by LLMs for identifying root cause locations. Next, look at the blue bars also pointing down in the top right panel. When we remove logs, type accuracy suffers. And this suggests that log text can contain important semantic clues that LLMs use to infer error types. And these two modalities are complementary and essential to better solve for the root cause. Now, on the other hand, when we remove traces, accuracy often improved. And this may be somewhat surprising, but trace alerts are often voluminous and noisy, and current LLM models struggle to filter this noise and often get distracted by irrelevant call chains. This brings us to research question 3. We didn't just want to know if the agents were wrong, we wanted to know why. And so to do this, we inspected the inference traces themselves, so not just the final answers. And we identified 16 distinct types of reasoning failures, which we mapped out in this taxonomy, which I'll show in a moment, along 2 dimensions. So first, we organized them by scope horizontally. So we were looking at, does the failure occur within a specific hypothesis? Does it span the full history of the trace? Or is it cross-cutting, so appearing anywhere in the process? We categorize them into 3 buckets. So we have our general reasoning failures, which are logical fallacies that undermine the overall credibility of the answer, like making a claim without evidence, or worse, hallucinating that evidence. RCA-specific failures, which are issues related to domain knowledge, like misinterpreting a metric anomaly or failing to follow triage heuristics. And then lastly, the procedural failures, which are issues with the workflow itself that cause procedural breakdowns in how the LLM functions as an agent, like getting stuck in a loop or stalling or frequently repeating itself. So with this taxonomy, we then use the LLM as a judge, so GPT-5 that I mentioned before, to quantify how often these occurred in a subset of LLM-generated RCA outputs. When we analyzed the prevalence of these failures, three clear trends emerged. First, the procedural failures were varied widely across models. So they were quite high for smaller models in the react and plan execute agentic workflows. So this points to the emergence of model-specific instabilities under agentic control, and it's consistent with those breakdowns that we saw in RQ1 for those same small models. Next, the RCA-specific failures were consistent across all models with very few differences between workflows. There was this very narrow spread. This points to a domain gap. There's an inability for these general purpose LLMs to perform RCA-specific reasoning, which indicates insufficient domain heuristics. But not only that, we observed widespread general reasoning failures. And the most common failure was actually evidential insufficiency, occurring in 80% of samples. This means that models frequently fail to back up their claims. They were often guessing rather than proving. And so the takeaway here is that RCA-specific reasoning remains insufficient and indicates lacking domain heuristics, and that general reasoning failures are still very much present. Finally, for RQ4, we asked, how is the presence of reasoning failures associated with the likelihood of generating correct RCA hypotheses? So we answered this by measuring the statistical association between each observed reasoning failure by the judge and the final correctness of that sample. And here's what we found. First, a small set of failures were consistently linked to large drops in correctness across tasks. So these include anchoring bias. So this is a failure where a model prematurely fixates on an early hypothesis and neglects to explore alternatives. Repetition or stalled progress. Here, the model loops or makes little forward progress. Arbitrary evidence selection is a failure where a model arbitrarily cherry picks or misuses evidence in ways that doesn't match any sort of systematic diagnostic strategy. And then lastly, failure to update belief. So this is a failure where the model does not revise earlier claims when later evidence contradicts them. So these failures are high impact in the sense that their presence is associated with substantially lower output correctness. Now, we also examined differences across workflows and found a clear trade-off. So agentic workflows tend to show smaller per reasoning failure negative associations. So iteration gives more chance for partial self-correction. So a single failure is less likely to fully derail the entire result. But agentic traces also contain more reasoning failures per sample. So longer traces allow for more opportunity for mistakes, and that increases reasoning failure co-occurrence and makes error compounding more likely. And so put together, the results suggest that while iteration can reduce the impact of any single failure on average, accumulation of multiple failures can still degrade performance. And this helps to explain why the agentic workflows did not reliably improve overall accuracy in RQ1. So eliminating early reasoning failures, or the ones on the left here, the strongest negative predictors of correctness, and controlling error propagation might be more impactful than simply adding more agentic structure. So let me walk through the key implications that emerge from these results from the 4 research questions. So first, we found that agentic workflows don't reliably improve accuracy. Instead, they introduce a practical kind of agentic tax. More steps means more opportunities for reasoning failures and also some added latency. And what really stood out is that small models in particular struggle the most with these multi-step workflows. This reveals a clear competency threshold. Below a certain capability level, adding agentic structure doesn't stabilize reasoning, it actually adds more instability. And so the design takeaway here is prioritize stability before adding additional complexity. Now, even when that competency threshold is met, model size alone doesn't solve the problem. Scaling size does help in one important way. Larger models are more stable procedurally. We saw much less procedural failures within those models from RQ3. They follow instructions better and handle agentic scaffolding more reliably, but they still make the same domain-specific reasoning and interpretation errors. So off-the-shelf LLMs lack the inductive biases of a reliability engineer and frequently ignore standard triage heuristics. Now, at the same time, we also see persistent general reasoning failures across all models. Failures like anchoring bias and failure to update belief have some of the strongest negative associations with correctness. Models commit too early, they fail to explore alternatives, or they don't revise their beliefs. And the takeaway is twofold. We need domain grounding, like fine-tuning on RCA tasks or embedding explicit domain heuristics and/or tools. But we also need to actively enforce good general reasoning behavior. For example, by encouraging early hypothesis diversification to combat that anchoring bias, or through structured search. So rather than just assuming that it will emerge automatically with model scale or from agentic structure alone. This brings us to the role of input context. So giving models more data didn't always help. In RQ2, excluding traces actually improved performance. And I think it touches on an important observation that more data is not always better. Context selection matters more than context length, and it's a matter of context engineering. We need to adequately summarize and filter and abstract information before the model ever sees it. And keep in mind that these results are even with our alert extraction procedure in place, where we're already picking out important signals. Now, finally, there's a deeper reliability concern around outputs that look plausible but aren't actually supported. So in our results from RQ1 and RQ3, we saw that models generate correct root cause hypotheses while hallucinating propagation paths or exhibiting severe reasoning failures like fabricated evidence. And these are essentially lucky guesses, right? The answer happens to be right, but the explanation isn't. And so correct guesses that are poorly justified or worse contain hallucinated explanations undermine operator trust. And this exposes a limitation of how we typically evaluate these systems, right? If we're only measuring final accuracy, we miss this underlying fragility entirely. And that's why evaluation needs to go beyond end labels and explicitly detect and penalize unsupported or poorly grounded reasoning, even when the final answer happens to be correct. So these implications point to a set of practical design priorities for our CA systems. So in short, future work favors simplicity unless model competence justifies complexity, focus on grounding agents with domain heuristics, prioritize selecting good quality system context, and expanding evaluation procedures that investigate and validate LLM reasoning, so not just those final labels. Now, before wrapping up, I'll cover the limitations and threats of this work. So first, we used a deliberately controlled setting to isolate reasoning. This means single fault scenarios, manually constructing knowledge graphs, and deterministic tools. So this makes behaviors easier to analyze, but it doesn't capture the full messiness of real production systems. For internal validity, some results are still sensitive to design choices like prompt phrasing or how the alerts and system knowledge was represented, and also how reasoning failures were identified. And these can all influence model behavior. And of course, our taxonomy and judging pipeline also involve a mix of human and model judgment. And we mitigated these effects by using multiple input representations to increase prompt robustness. And we used a strong model. We used GPT-5 for the judge and performed that human reliability check to check the reliability of the judge results. But still, some subjectivity is unavoidable here. And then finally, for the external validity, we evaluated a limited set of benchmarks, open source LLM models and workflows, so the findings may not fully generalize to large-scale production level systems or proprietary models. But to support replication and extensions, we do plan to release all the code results publicly. Now, overall, I think these results should be interpreted with these caveats in mind, but we do believe that the controlled setting that we experimented with in this work still yields useful and actionable insights into reasoning patterns and system design trade-offs. So to conclude, we asked how well LLMs can actually perform the core task of RCA when removing confounding factors. And we found that while LLMs can produce plausible diagnoses, agentic complexity and additional data do not reliably improve accuracy and can actually introduce hidden fragility. And even at larger scales, persistent general reasoning failures like the anchoring bias and the inadequate hypothesis exploration, these remain common and persist and are strongly associated with incorrect outcomes. So reliable RCA therefore requires more than just raw reasoning power or model scale. We still need domain grounding and careful context selection and stability-focused design. But they must be paired with mechanisms that actively enforce good reasoning or general reasoning behavior. And I think most importantly, high-level accuracy alone is not sufficient, right? Models can be right for the wrong reasons, which undermines operator trust in real-world settings. So taken together, these results suggest that future RCA systems should prioritize robustness and interpretability and targeted domain structure before adding more complexity. So in short, better RCA won't just come from piling on agents or context, but from building systems that reason carefully, systematically, and transparently. All right, that concludes my thesis presentation. Thanks so much for attending and everybody online as well. I now open the floor to any questions.